So in the previous session, we have seen the specific heat of different specific heat of gases, and next we have seen that for an adiabatic process, the equation of state is PV to the power gamma, where gamma is the adiabatic exponent. Then we expressed Cp and Cv in terms of gamma. Now let us take with some examples, see how to use first law for a gaseous system and how to express a process in a PV diagram and how to extract information from it. So take some examples. So example 1. So in this example, we have taken an ideal gas kept inside a vessel. So this is an ideal gas whose adiabatic exponent is gamma, and this is adiabatic boundary wall, so that no heat can go inside and it can come outside. So delta Q will be equal to 0. So what we want, suppose this whole vessel is moving with velocity v and it is suddenly stopped. So it is suddenly stopped here. So now it has no velocity. So the gas here, the temperature of the gas will increase. So to what extent, what is the increment in the temperature of this gas if this gas is suddenly stopped? This is a question. So what is the increment in the temperature of the gas, the vessel is completely stopped. So you see here, let us apply the first law to it. Delta Q is equal to delta U plus delta W. So here, since the volume is fixed, this wall are rigid, adiabatic rigid wall, so there is no work done in the system. So dq is 0, delta W is 0. So what happens? So the internal energy delta U plus, you see, work done is change in kinetic energy. So there is no configurational work plus this dissipative work. So what happens? There is no configurational work in the system, but what happens that delta U is the kinetic energy of the system gets converted into that work, that is the dissipative work done. So that is actually minus half mv square. So the total kinetic energy gets converted into potential energy. So there is a rise in temperature. So we say that here delta U will be equal to half mv square, where m is the mass of the gas inside it. So delta U is equal to n Cv is R by gamma minus 1 dt, that is equal to half, m is the mass of the gas, into V square. So n number of moles. So we can write this mass as n number of moles into molar mass into V square, n cancelled. So we have dt is equal to mv square gamma minus 1 by R, where m is the molar mass, v is the velocity, gamma is the adiabatic exponent, and R is the gas constant. So you see here, so when this system is moving in this frame, when we suddenly stop it, we did some work on that system. That is of course not the configurational work, that is the dissipative work done. So here, this is a very important example. So how much work is done on the system is half mv square. So dissipative work done by the system I have written as minus half mv square. So why minus? Because actually the dissipative work done by us on the system is half mv square. So by the system it becomes minus half mv square. So is this expression. So now let us take up another example. We have two vessels, thermally insulated vessels. This is, and there is a valve connected so that they can communicate. So here the volume is V1 and the pressure of the gas inside is P1 and it is P2 and V2. They are thermally insulated. So we have two thermally insulated vessel with P1 V1 and P2 V2 as their thermodynamics coordinate, as their thermodynamic coordinates. That means the conditions are here P1 V1 and P2 V2. Now find the final pressure and temperature. Initially their temperatures are the same. Find the final temperature and pressure after opening of the valve. So now we have two gases in this system in which P1 V1, and let us take temperature as T1 T2, not the same, and see that when we open it, then how the gases will mix up and what will be the final temperature and pressure. You see, this is adiabatic walls. That means no heat comes from outside, and this is not only adiabatic walls and rigid wall. That means the volume is also not changing. So in this case, the total internal energy is going to be the same. We will use that property. Now you see, the internal energy initially U1 and this is U2 is equal to U mixture. That is, once we open it, then after opening, the equilibrium condition is that they have the same pressure and T and the same gas we have. So suppose, let us assume their gamma is the same initially, same gas is there, and so finally the gamma is the same. So here let us find how much gas is initially. So N1 number of moles will be there, that will be given by P1 V1 by RT1. And how much moles of gas will be initially present? N2, that is equal to P2 V2 by RT2. So we have N1 number of moles as P1 V1 by RT1 and N2 is equal to P2 V2 by RT2. So now we have U1, the internal energy of this gas, as N1 RT1, this as N2 RT2, and U is N1 plus N2 RT. So here R, this R cancels, this R cancels. So N1 T1 plus N2 T2 is equal to N1 plus N2 T, where T is the final temperature. So the final temperature we got is N1 T1 plus N2 T2 by N1 plus N2, where N1 and N2 are given by this. So if I substitute N1 N2, so N1 into T1 is equal to here P1 V1 by R. This term is equal to P2 V2 by R. N1 is again P1 V1 by RT1 plus P2 V2 by RT2. So thus you see that we have T final as this R can be cancelled. So we have P1 V1 plus P2 V2 P1 V1 plus P2 V2 into T1 T2 by P1 V1 T2, P1 V1 T2 plus P2 V2 T1, P2 V2 T1. So this is the final temperature. So I will write this as T final. Now once I know T final, I can tell what is the pressure here. So pressure P1 dash is equal to, now here pressure will be, the number of moles will be equally divided. So it will be N1 plus N2 by 2. So equally pressure will be divided. N1 plus N2 by 2 are T final, and pressures will be same. So this pressure and this pressure is same, so no need. Final pressures will be directly written as P final is equal to that number of moles N1 plus N2 or that is T final by volume, that is V1 plus V2. So we have this equal to N1 plus N2, that again P1 V1, that is again P1 V1 by RT1 plus P2 V2 by RT2 into R T final. T final we will get from here plus V1 plus V2. So this is our final pressure and final temperature in this vessel. Now let us take one more example. Nu moles of a certain ideal gas at a temperature T0 were cooled isochorically so that the gas pressure reduced n times. Thus, as a result of the isobaric process, the gas expanded till its temperature got back to its initial value. Find the total amount of heat absorbed by the gas in the process. So let us first draw its PV diagram. So this is P, V, and this is P. So nu moles of a certain ideal gas at a temperature T0 were isochorically. So T0, let us assume an isotherm of temperature T0. So this isotherm has a temperature T0, and nu moles of a certain ideal gas at a temperature T0 were isochorically cooled isochorically so that the gas pressure reduced eta n times. So here suppose isochorically means volume constant, and so here pressure was initially P0, so it has become P0 by n times. So n times its pressure was reduced. As a result of the isobaric process, the gas expanded till its temperature got back its initial value. So now after isochorically expanding it, now it is isobarically expanded so that it got its temperature back. So this is the initial position and this is the final position. Find the total amount of heat absorbed by the gas in the process. So how much is the total heat absorbed in the process? You see, since the initial and final positions are on the same isotherm, same temperature, so there is no change in internal energy. So we have delta U is equal to U final minus U initial is equal to 0. So using first law, what we got, delta Q is equal to delta U plus delta W. Delta Q is asked and delta U is 0. Now work done. Now work done, this is suppose point O. So work done in I to O plus work done from O to F. So delta Q is required, this is 0, plus work done, this is isochoric process, so no work done. This is now work done from O to F. You see, this is area under this curve. So area under this curve gives the work done during O to F. So this is suppose V1, this is V2. So we have area under curve as P naught by N into V2 minus V1. So we have delta Q is equal to P naught V2 by N minus P naught V1 by N. Now PV by N is equal to, you see here, this is P naught V2. So P naught by N is the pressure at this place, P naught by N and V2. So this quantity P naught by N is the pressure at V2, that is P2 V2, that I will write as nu RT naught minus P naught V1. P naught V1 is again nu RT naught by N. So we have this equal to nu RT naught 1 minus 1 by N. So this is the delta Q, that is the heat transferred to the system. Based on this heat input, the system is capable of doing work and on the outside environment.